Hello, and welcome to this video on the binomial theorem. I'm actually just going to do an example of applying the binomial theorem. But we talked in class a bit about how the binomial theorem is related to counting problems where you have some number of items and then you choose some number less than that from them. And we also talked about how it's related to Pascal's triangle. We're going to see both of those. I thought the best way to do this would be by using an example. So we're going to take this example where we're going to look for 2x plus 3 to the fifth. Now, if you were doing this in algebra class, you would probably do this like this. 2x plus 3 times 2x plus 3. That would give you 2x plus 3 squared. And you would do 4x squared plus 12x plus 9. That's great. Now you have to multiply that by 2x plus 3 again. Take that answer, multiply until you've done that, until you've written this out 5 times. Until you've done, so you do the third time, then you multiply that one to get a fourth time, multiply that answer to get a fifth time. It's a lot of writing out, and if you're like me, you'll make a mistake along the way and add something wrong or skip a term or something like that. The binomial theorem is a shortcut to expand. This is called a binomial. This is a two-term polynomial. So the binomial theorem shows you how you can expand a binomial raised to a power. So I'm using the fifth power here. And the binomial theorem says, okay, this is my n. So I start with n choose r, where r is 0. And notice the n's are the same all the way across. I choose 0, then I choose 1. Remember, 0 factorial is 1. By definition, don't argue with me about that. It's an I said so thing. So I said so, so it is. It's really not because I said so. I don't have that much power, but you know what I mean. It's a mathematical understanding that 0 factorial is taken to be 1. So n is 5, r is 1. So we can calculate all these. We learned how to calculate this using this. Now this is a combination, not a permutation, so that r factorial does appear in the bottom. So what you're going to see is you have some symmetry. You know, choosing 0 is the same as keeping 5, and choosing 5 is the same as leaving out 0. So the ones that, you know, the n's, this number is going to come out the same. That's always going to be a 1. Anything choose 0 is a 1. Anything choose itself is a 1. You always get that. But when I apply this formula to each of these coefficients, this is where the coefficients come from. The pattern that the variables follow are whatever was first is called a. So I have a to the nth power, b to the 0th, b to the n minus n. And this is, so this is a to the n, b to the n minus n, or n minus n, or b to the 1 in the bottom, okay? Here, the a becomes the fourth. 5 minus 1 is 4, but these two exponents always add up to 5. See that? So then the exponent of the a goes down by 1, the exponent of the b goes up. So I use this generic example of a and b to set up to figure out our coefficients, so you can see where they came from. So here are your coefficients. They come from evaluating this. 1, 5, 10, 10, 5. And you see the symmetry. 5 choose 2 is the same as leaving out 3, and 5 choose 3 is the same as leaving out 2. So here you're choosing 3 to leave out, here you're choosing 3 to leave in. There's still only the same number of ways to do that. That's where you get the symmetry. If we had an even power, notice also we get 6 terms from it. We get n plus 1 terms. So anything to the fifth, we will have 5 plus 1 terms. We'll have 6 terms. Just like if you do a plus b squared, and the number you're going, that's a squared plus b squared. It's only 2 terms. It's not. It's a squared plus, just like I did above, 2ab plus b squared. You get 3 terms out of squaring a binomial. You get 6 terms out of raising a binomial to the fifth. So you get all these coefficients, and I just left the patterns. Now b to the 0 is a 1. A to the 0 is a 1. So I just left them out in these n terms. And you can now see the pattern. But I need to find, I found a plus b to the fifth. I need 2x plus 3 to the fifth. So 2x is a, and 3 is b for my problem. So if I scroll down here, you'll see, and this takes some really careful bookkeeping. I left out the 1 because 1 times anything is just the thing. So here's your a to the fifth. Here's your a to the fourth, b to the fifth. There's your coefficient of 5 right there. So a is 2x to the, now if b had been, if he had subtracted 3, b would be a negative 3. So I follow this pattern all the way through, and then I have to be really careful with my algebra. 2x to the 5th is not 2x to the 5th. It's 2 to the 5th, x to the 5th. Little algebra reminder there. Same thing here. I've got 2 to the 4th, x to the 4th. So I get the 240 from 5, and that'll be a 4 times 4 times, that won't be a 4, that'll be a 16, I'm sorry, 16, 2 to the 5 times 16 times 3 is where that 240 comes from. If you do out all of these numbers, you can stop the video and try it yourself if you don't believe me. This is what you get for answers. So notice there's no b in this because b was a number. This number gets incorporated into the coefficient. If I were looking for another way to do this step, rather than doing the n choose r, where I get the 1, the 5, the 10, I could look at Pascal's triangle, and that's what I've got down here. This is a nice picture of a Pascal's triangle. What it's nice about it is it labels it. With Pascal's triangle, you start counting at 0. A lot of times in computer science, we start counting at 0. And in number theory, we start counting at 0. So the 0th row, if you had started counting at 1, you would have only used this row here, and that wouldn't have been correct. That would have given you 2x plus 3 to the 4th. Here's your 5th row. You must start counting 0. So there's your coefficient. 1, 5, 10, 10, 5, 1. And you have to know that this is, This is a to the 5th, b to the 0. This one is a to the 4th, b to the 1st. This is a cubed b squared. See what I'm doing? I'm going down 1 in the power on a and up 1 on the power of b, until finally the a is missing in the n term. That's not squared, sorry, that's b to the 4th. And this last term will be b to the 5th. So this is just a to the 5th here because the b to the 0 will give you a 1. This is where the coefficients are found in Pascal's triangle. You saw you had something raised to the 5th power, so you go to the 5th row, remembering to start counting at row 0 if you have the whole triangle in front of you. And if you want to check that, remember what the pattern is for something squared. It shows up in, if you start counting with 1, it shows up what's the 3rd row. You have to start counting with 0. I hope this helps you understand binomial theorem a little better. It is quite useful. There's a lot of other uses for it, but this is the algebra use for it. And thank you for joining me.